Hi, my name is Damir Youlavoie and I'm a PhD student at McGill University. I'm going to present our paper on Monte Carlo method for fluid simulations. In computer graphics, Monte Carlo methods have been used extensively in physically based light transport, where they outshine traditional finite element methods by their simplicity, parallel scaling, and robustness. The trade-off, instead of getting a one-shot clean image, we get a sequence of noisy images that gets better over time. For this reason, they were initially considered slower than their counterparts, as the noise can take quite some bit of time before vanishing completely. Luckily, their ridiculous effectiveness at handling challenging radiometric effects, such as complex geometry and advanced reflectance models, made them a favorite of the movie industry. Additionally, recent advances in Monte Carlo ray tracing methodology, image denoising, and supersampling enable the use of such method in real-time applications. It shows that up to this day, Monte Carlo rendering still benefits from an active research. The field of geometry processing recently went the same way by adding the Walk-on-Spheres algorithm to their toolbox, complementing their traditional finite element solver. The reasoning was that many geometry processing applications require high-quality meshes to work out. Sadly, a high-quality mesh contains a lot of triangles, and when used in numerical solvers, give rise to large linear system that takes many gigabytes of memory and up to days of computing to resolve. In such cases, an approach using the Walk-on-Sphere algorithm can instead give back noisy results in a matter of minutes and with an order of magnitude less memory consumption. Being robust to geometry, the Walk-on-Spheres algorithm gives back good results even without having access to a high-quality mesh. This is a nice feature since they are not so easy to cook up anyway. Additionally, this change of perspective also had interesting side effects in other fields. For instance, this new approach served the rendering community by accelerating the computation of subsurface scattering and offering a novel way to generate diffusion curve images. Similarly, Monte Carlo methods themselves benefited from our community through the development of new variance reduction techniques, such as the celebrated multiple importance sampling method and a brand new bidirectional Walk-on-Spheres algorithm, to name a few. Motivated by the unique properties of Monte Carlo method and its growing adoption, we were really curious to see if another pillar of computer graphics could benefit from this super awesome framework. Of course, we are talking about fluid dynamics. Similarly to its peer, most of the state-of-the-art methods are also finite element based. While many other approaches exist, they are all based on the same principle of discretize and solve everywhere. Thus, they typically need to solve multiple linear systems that get harder and harder to solve as the scene complexity increases. Some theoretical papers propose stochastic interpretation of fluids governing equations. However, none of them resulted in a viable numerical method since they were only concerned by the existence and boundness of solutions. Our proposed method partially built on one of these work. In practice, fluid simulations are rendered using Monte Carlo ray tracing. Thus, we thought it would be interesting to have an end-to-end simulation rendering pipeline where Monte Carlo properties are present at all stages. Also, since Monte Carlo methods are pointwise by nature, it will offer us a way to simulate only what is seen without worrying about the full scale and complexity of the scene. While we weren't quite able to achieve this goal yet, we laid the foundation to do so. More concretely, our contributions are a recursive pointwise probabilistic solver for 2D Euler equation using Biot-Savart, a practical-based formulation, a cache-based formulation to overcome the exponential cost of this method, a Walk-on-Sphere treatment that handles free slip boundary conditions on bad geometry using the stream function, a generalized probabilistic solver for the 3D Navier-Stokes problem using the Feynman-Kac formalism, applications of Monte Carlo variance reduction for the first time in fluid simulation, and finally, a roadmap of open challenges that will make it scalable in the future. Before we get our hands dirty with the how of our proposed approach, we'll briefly summarize the Monte Carlo methods mentioned earlier and the problem we are trying to solve, namely the dreaded Navier-Stokes equations. The reason is that while some of you may be familiar with Monte Carlo, they might not be so with fluid dynamics and vice versa. We don't want that to hinder you along the way since our goal is to reach as many people as we can. The first Monte Carlo method that we will discuss is Monte Carlo integration. It is a stochastic method employed to approximate integrals. Here, stochastic means that we use random samples. It goes as follows. First, you sample uniform random point in the domain of integration. Then, you average their contribution and scale the result to account for the domain area. In essence, this is like the usual deterministic quadrature approach, but with error showing up as noise instead of bias. This method shines when you consider some of its variance reduction techniques. First, observe that we don't need this sample to be uniformly distributed. In fact, it can follow any distribution that we want. This choice greatly impacts the method's efficiency, and choosing a distribution that is proportional to the integrand will reduce the amount of noise in the result at equal sample count. Doing so is called important sampling. Another technique is called antithetic sampling. Basically, when the integrand is antisymmetric, you can sample point in antibodal pairs instead of one at a time. Doing so will decrease the amount of noise so long as the antisymmetric property is satisfied. Finally, we have the control variant technique. Basically, if you already know part of the integral solution, you can just extract it. Doing so will reduce the variance of the solution if done carefully, such as when the difference is close to zero or easy to important sample. Another Monte Carlo method is the so-called Walton-Spheres algorithm. It is a method that was recently introduced to computer graphics by the geometry processing community. It gives us a recursive stochastic approximation to the solution of Poisson equations with Dirichlet boundary condition, meaning that we prescribe values on the boundary. These equations are ubiquitous in mathematics and physics and appear in many computer graphics applications such as gradient domain, surface reconstruction, and pressure projection in fluid dynamics. Let's go back to the Walton-Spheres algorithm. One way to derive it is to use the following identity. First, consider a point of interest and a ball surrounding it that fits inside of the domain. The first term is a volume integral over this ball. Its role is to account for the source function contribution of the Poisson equation by convolving it against the harmonic green function. The second term is a contour integral over the ball boundary. It is there to capture the flux of the solution. Here, the convolution uses the harmonic Poisson kernel, which is the normal derivative of the harmonic Green's function at the boundary. From this second integral, we get a recursive relation. And to avoid solving such a difficult integral equation, an approximation using Monte Carlo integration is used. More concretely, we follow the recursion as follows. First, we start from the position of interest and find the largest sphere that still fits inside of the domain. We then sample a random point inside the sphere and add its contribution to a running sum. Then, we sample a new position on the sphere boundary. Once done, we find the largest sphere around this new point, and then we iterate this process of adding and sampling until we get close enough to the boundary. Finally, we add the nearest boundary value to the running sum and terminate the recursion. With some minor modification, this approach can even be made to approximate the gradient of the solution directly. The problem we want to use these Monte Carlo methods on are the incompressible Navier-Stokes equation. More specifically, we are interested in the vorticity formulation of these equations. While they may seem daunting, all we really need to know from them are the meaning of its individual terms. First, there's the vorticity definition. Intuitively, it describes the local spinning motion of fluid parcels. When solving for fluid motion, we need to infer velocity from vorticity. To do so, we can use the Biot-Savart law, which is just an integral of the vorticity with some domain-dependent function called the Biot-Savart kernel. Then there's the advection term. It describes how vorticity moves along the underlying velocity field trajectory in time. This is the Laplacian term, and it represents diffusion and describes how vorticity spread in space due to viscosity. And finally, we have the stretching term. That one is a bit annoying and is only non-zero in 3 dimensions. It's basically there to account for the angular momentum conservation. If that means anything to you, it's just so that when a vortex filament changes in length, it will adjust its local vorticity so that the totals stay the same. In addition, we must also prescribe initial and boundary conditions, otherwise the problem will not be well defined. We are now up and ready to discuss the basis of our method. While we deal with the full Navier-Stokes equation later on, we'll first consider this simple problem called the Euler equation, since it's a bit easier to understand. The problem is equivalent to assuming that the fluid is inviscid, so that there's no diffusion, unbounded, so that we do not have to worry about boundary condition, and that the domain is two-dimensional, so that no stretching occurs. We handle advection via a semi-Lagrangian scheme coupled with forward-Euler time integration. We use the forward-Euler discretization for its simplicity, but other schemes such as Runge-Kikuta method also work. Note that these are just fancy words to say that we look where the particle was before reaching the current position and set the vorticity to be the same. Now we replace the velocity term from this formula with the Biot-Savart law mentioned earlier. As a result, we get this recursive integral with respect to vorticity. All we propose to do is to solve this integral through Monte Carlo integration. In fact, this is quite similar to what was done for the rendering equation in the early 90s. That's it. That's the core of our method. All we have to do to know the vorticity at a specific point in time is to follow the backward recursion until we reach the initial condition and use it to set the solution. This is pretty similar to what the long-term advection method in fluid animation literature did, only with a bit of Monte Carlo sprinkled over it. We call this backtracing, and no special discretization is needed. Of course, we need to add back all the stuff that we omitted before, but the overall idea behind the approach stays the same. Oh, there's one small catch though. This method has an exponential cost in time. To see why, suppose that we wish to compute the vorticity at this position. To advect this point backward in time, we first need to know the velocity at this position, but at the previous time step. To do so, we need to compute the vorticity at this new sample position, which means that we have to compute the respective velocity at the previous time step. And this in turn requires us to determine the vorticity at these new positions. And thus, an exponential complexity emerges from this recursion. While this is far from ideal, we can circumvent this by using a cache to store computed values, as we usually do for recursive method with exponential cost. In this work, we use the uniform grid for its simplicity, but other more promising type of cache are also possible. Now, let's add back the rest of the stuff. First, we focus on the boundary conditions. A common condition used in computer graphics is the free slip boundary condition, which means that while a fluid is not allowed to cross the boundary, it can slip on it without friction. Sadly, we cannot use the Biot-Savart law like before because the Biot-Savart kernel is domain dependent and only admits closed form solution for super specific case like an unbounded domain. Instead, we first observe that a stream function, defined as the curl potential of the velocity field, always have levels set parallel to the underlying velocity field. The idea is this: force the stream function to be constant along the boundary so that the normal velocity component is 0. Using this condition and plugging the stream function inside of the vorticity definition, we get a Poisson equation with Dirichlet boundary. And to get back that stream function, all we need to do is to solve the system. How nice is it that this is exactly what the Walken sphere method do? We can even get directly the velocity back using the derivative estimator that we mentioned earlier. Now let's add back diffusion and stretching to the equation. To do so, we need a little something called the Feynman-Kac representation. That part is a bit more complicated and needs higher mathematics to get through, and for this reason, we will not go into too much details here. Intuitively, this formula transforms our deterministic partial differential equation into a set of coupled stochastic differential equations that are moving in opposite direction in time. One of them, the one moving backward, handles advection and diffusion, while the other handles the stretching of vorticity. In practice, we only need to add 2 steps to our previous approach. First, we advect backward in time as we did before, and depending on the boundary conditions, we can either use the Biot-Savart approach or the stream function one. However, this time we add a bit of Gaussian noise to the advected position to account for diffusion. And then, starting from the initial condition, we move forward in time, tracking the stretching deformation along the way. We compute this deformation using the vortex segment method for its robustness, but other approaches are also possible. Now let's look at some results. Note that all of them use some form of importance sampling. For instance, the Biot-Savart formulation uses vorticity field as an importance function since it's readily available from the cache. For the stream function formulation, with the first step of the Walken sphere gradient estimation uses antistatic sampling, while the rest importance sample the Green's function. For the advection scheme, we use Runge-Kutta and Euler discretization for the Biot-Savart and the stream function approach, respectively. First, we compare our method against 2 well-accepted approaches representing particle and grid-based solver. From left to right, we have increasing time along the simulation. And from top to bottom, we have our method, the vortex particles method, and flip. While our approach is admittedly slower than its counterpart when using such a simple geometry, its results are consistent with its peer. Next, we look at some 2D example of our stream function method. From left to right, we have 2 vortices propagating in a maze, a flow inside a more complex bunny-shaped boundary defined using a sign distance function, and vortices flowing around a solid obstacle in a periodic domain. It turns out that by setting the boundary value to be non-constant on part of the boundary, we can extend our Walk-on sphere approach to handle inflow and outflow conditions. Similarly, we can even support rigid body motion. Here, we simulate two interacting vortex rings with a cross-section visualization to illustrate the interior flow. Using past frame information, we devise a control variant and importance sampling strategy to make our method more efficient. Note that this is the first application of control variant to fluid simulation, and it is only made possible by our Monte Carlo framework. Here, we advocate a constant density at the bottom according to the velocity field simulated with our method. Then we render the result fully on top and with a cross-section visualization at the bottom. When the number of samples used is small, the application of control variant produces results that are closer to the reference simulation compared to the results without control variant. Here, we passively advocate a constant density field toward a closed mesh on the left and a triangular soup on the right. As expected, our method does not need clean geometry to work well, which is something that is generally difficult to handle with other approaches. And finally, our approach can also take into account tiny obstacles. On the left, we have a subgrid fence affecting the fluid flow, and on the right, we have a subgrid size square. To conclude, we presented a Monte Carlo solver for fluid simulation. However, this is only the beginning. Indeed, some problems still need to be addressed to unlock the full potential of this approach. We now list a few of them. The biggest hurdle right now is the tackling of exponential costs. Indeed, the use of a regular grid bias our estimator since we need to interpolate values that fall in between cells. This results in energy dissipation that propagate in time, dampening the simulation. We believe that alternatives to this approach exist and are worth investigating. Next, the semi-Lagrangian advection method is also a source of bias because of its the underlying nonlinearity of the vorticity field. Finding a better approach here still remains an open question. Supporting a wider range of boundary conditions, such as stick and free boundary, will also be interesting. Doing so will probably rely on a Poisson equation with Neumann boundary condition instead of Dirichlet. Sadly, there's no efficient way yet to solve that through the Walk-on sphere method. In addition, our stream function formulation has subtle limitations in 3D that still need to be addressed. It will also be interesting to reframe our method in the context of other Monte Carlo technique. And finally, let's not forget that we still need to unlock the ultimate goal of this method, namely to unify the simulation and rendering of fluids motion. That's it for today, and thank you for listening.